So this is not difficult. I mean, you have x and y. You take set S be the minimal non-empty set, say subset of x such that size of S is as big as its neighbor of S. See that the x satisfies this. So neighbor of x is exactly y, because this is non-trivial and there is no isolated vertices. So every vertex y has a neighbor. So x satisfies this condition. So we can find the minimal one. So x satisfies this condition. So we try to kick out each one of them. And then if none of them satisfy this, then x is our choice. Otherwise, you change it to the smaller one. You keep do that until you hit the last one which satisfies this. Then by the minimality, when we have S and neighbor of S, so let's say y here. By the minimality for every subset S prime, which is S, for every subset S prime, we can show that the neighbor of S prime is bigger than or equal to the size of S prime. Yeah. You can actually show this, and then for S itself, its size of S and its size of neighbors are same. If this is S is strictly bigger than the size of this, then you can actually delete one vertex from S, where keeping the definition, so it contradicts to the minimality. Anyway, so we can actually show that for this S, for any subset, we can find this. We can prove this property. But this is exactly Hall's property. So we can find the matching covering the vertices of S and vertices of exactly the vertices of NS, because S has size same as NS. Then this is the exactly matching, which doesn't have no such edge between S and outside. So which is exactly the vertex set which cover S and its neighborhood. So with this, we can prove the theorem. So let G be an XY bigraph with, say, X as large as Y after discarding possible isolated vertices. Then what we claim is that this statement we claim for given bipartite, say, multigraph G, there exists a proper edge coloring C such that the orientation DC of LG, the line graph of G, which is defined as before, as in the previous lemma, this satisfies T plus in this orientation, its out degree is at most the maximum of degree of x in G and degree of y in G minus 1 for each edge of G. So if we prove this claim, then what do we know? Previously we showed that, where is it? Such orientation, this DC, the resulting orientation is kernel perfect. We know that's kernel perfect. And then also in this orientation, with f being defined out degree plus 1, it is f choosable. So if we somehow find the C, which guarantees that this DC, which is kernel perfect, orientation, and its maximum degree satisfy this. So if we take the plus 1, then that's exactly the value of this f. So the lemma says that the line graph is f choosable. So which is exactly what we want. So it suffices to just prove this lemma. Following claim. So it all boils down to prove this claim. So we use induction on the number of edges in G. So base case is if G is a perfect matching, then use one color. So we are done. If we use just one color here, and then let's say everything is 1, then in LG, the line graph of G, you have E1, E2, E3. So this is DC, and this is just all isolated vertices, which satisfy out degree 0. Let's say this is D, and EI is 0, which is maximum of 1, 1, minus 1. Because this vertex has degree 1, this vertex has degree 1, you take the maximum and subtract 1. Now we take the induction. For the induction step, let M be matching as above. Matching as guaranteed by the previous lemma. And let G prime by be the graph we obtain after deleting this. And let C prime be the edge coloring of G prime guaranteed by the induction hypothesis. And we extend this C prime to a proper edge coloring C of G by giving the edges of M a color larger than all the colors used in C prime. So remember, C is just any proper edge coloring. We don't have any restriction on how many colors we use. It's just some, tool to get the orientation. It's not actual edge coloring that we want to use. It's some tool to get the orientation. So we only want to get this orientation. So what it says is that if we have this G and you have this M, which consists of E1, E2, E3, and you delete that to get the G prime, then you get this L of G, and you don't have this E1, E2, E3 in this L of G prime, so this is deleted. And then in the remaining one, you have this orientation defined by C prime. So you delete this, and then this remaining H is G prime. So G prime is G minus M. So let's say G is including blue graph, and G prime is just the black one. For this G prime, by induction hypothesis, there is C prime. And by using this C prime, we can consider this, C prime gives, say, 1 here and 2 here, then this is X and this is Y. Then what was the definition of D prime before? D sub C prime. D sub C prime is that these two are sharing the, say this is 3. And let's say this A, B, C, not C, A prime, B prime. Then here, if we have, again, AB, A prime B, AB prime, then AB and AB prime, they share the vertex X. So you orient it from the, smaller one to larger one. And AB and A prime B share the vertex in Y. So you orient it from a bigger one to a smaller one. So for this certain C prime, you get this. And then here, what you know is that this holds. So here, T plus T prime, let's say this is T prime, XY is at most maximum of TG prime X, TG prime Y minus 1. And now you put these blue edges back and then give them some color, which is say 100, which is larger than any other numbers which is used by this C prime. Again, remember, we don't care how many numbers we use on this C or C prime. So, the orientation TC prime is actually obtained from TC. So we also have a TC here. By giving this all 100, now we know how to orient edges between these two. Let's say E1 and here. This is 100 and this is 2. And then 2 is small, and they share the vertices in Y. So you orient from big to small. So this orientation D prime, which is DC prime, is obtained from DC by deleting these vertices. Vertices, which is related to M. And if you passing from DC prime to DC, the vertices whose out degree increases are, so this vertex doesn't, the out degree doesn't increase, right? Because it has one more in neighbor. R, but if you have this edge, then its out degree increased by 1. It used to have like C prime value 10, but now this one has a larger, larger C value. So let's say this is E, then E to say E3, you have an, edge directed this way. So its out degree increase. R, they are incident to vertices in X, which is covered by M, and their out degree increases by 1 as M is matching. So for such an HXY, we know that the degree of both XY is, both X and Y is larger by 1 in G than in G prime. Since M, by the choice of M, it covers all neighborhoods of its endpoints in X. Hence, the condition on out degree continues to hold outside M. So all the edges, all the red edges or green edges here, they all, satisfy this condition. Now we only have to check the condition for H in the matching. If XY is in M, then what do we have is we have its out degree in this C, XY, is same as the degree of vertex Y in here. Because we gave the large number here, so if we have some H, E, then all of these green edges, which shares the vertex X, have a smaller C value. So if this is E prime, then E to E prime is directed this way. So they are in neighbors in DC. And all these purple edges are, on the other hand, out neighbor of E. Because, it has a smaller value than E in C, and then they share a vertex in Y. So in DC, which is the orientation of line graph, E is, directed from E to E double prime. So we have this, which is at most the maximum of degree of x and degree of y maximum minus 1. So this finishes the claim. So this shows that we can find certain proper edge coloring C such that the orientation DC we obtain from this coloring C is, we know that which is kernel perfect, and it satisfies this out degree condition. And we know that if for each vertex xy in line graph of G or edge xy in G, if we give the list whose size is 1 bigger than its out degree, then we can finish the coloring. So we can prove that for this specific function xf, we can actually prove that this, G can be, line graph of G can be colored with this condition. It is f choosable. So now we are ready to prove the statement that we want. So if G is a multigraph, then we can show that its edge list chromatic number is at most 1.5 times its maximum degree. So let L be a list assignment. So what we want to do is we want to find some partition, and we consider this edge and this edge and this edge. So this is not bipartite, but we already have some statement about bipartite graph. So what we want to do is we want to first color these purple edges. And then once we color these purple edges, some colors in the list of each edges here may not be available now. Now we delete those edges, which is possibly dangerous. Then list size reduces. But at the end, we want to show that it reduces to certain point, but not too much, so that we can finish the remaining, coloring. So for that, we want to first make sure that there are as many cross edges as possible, and there are as small purple edges as possible. So we have a list assignment for the edges. And let H be a bipartite graph. Bipartite subgraph. Of G with the largest number of edges. Then what do we know is for each vertex B in this graph G, we have that the degree of V in H is at least half of the degree of vertex in G. So if this doesn't hold, so first it's easy to show that this H must be there must be some partition A and B, and H must be all the edges between. And if there is one vertex here, which only sends, say, one edge here, but two edges here, then what you do is you just move this to other part. Then you get a graph with a larger number of, you get a bipartite graph with larger number of crossing edges, a contradiction. So we can actually show this inequality. And let H prime be the remaining purple graph. And because of that, we can actually show that this H prime has maximum degree at most half times maximum degree of G. So each purple edge here is incident with delta over 2 minus 1 edges here and delta over 2 minus 1 edges here at most. So each xy each edge, say, of H prime is incident to and most, say, delta of G minus 2 edges, 2 other edges. And we know that, say, so our assumption is that this list assignment satisfies that each edge there are at least 1.5 times maximum degree of G many available colors for each UV in the graph, edge of G. So we can, just easily choose a proper coloring for this H prime. So we can color all the edges, in H prime. And for on HXY in H, we form the new list L prime by deleting from the original list. We delete the colors used on edges incident to X and Y. Then the size of this new list is at least 1.5 times maximum degree minus degree of X in H prime and degree of Y in X prime. And since degree of X in H prime, say Y in H prime, is half times the degree of Y in G and almost half times of the maximum degree. So we have that this L prime XY is at least maximum degree times the degree of X in H prime. But in that case, this is what? Degree of G minus X, G of X minus degree of H prime of X, which is a list of the degree of X in H. And by the similar way, you can change this to X and this to X, and then this to Y, this to Y, and this to Y. This list also has size at least degree of Y in H. So by the previous theorem, the edges of H can be properly colored from what remains of the lists on its edges to complete an L coloring of G. So because we only now have to the color here, and then we can forget the edges here or color because it's automatically encoded in the remaining list. So we can choose the colors so that they are proper coloring in H, and which automatically finishes the L coloring. So yeah, this is all for today. Thank you.